Done.
Right. Yeah, we are online.
Okay. So thank you for this attending this session. We're happy that Professor Subhash Chaudhary is also here. Former DD is here. And Professor Ghosh, who is very closely connected with the work of Haldane, has kindly agreed to give the opening remarks. And Kedar is here, so who was responsible for getting Professor Haldane to this function. So I'm very happy that all of you are here. I request Professor Ghosh to give the opening remarks, and then the two speakers will give the talk. Thank you.
Professor Chaudhary and all friends. This morning when Professor Suresh invited me to give some opening remarks, I accepted it because my connection with the topic of today's talk is older than the age of one of the speakers today. And so Professor Haldane shared the 2016 Nobel Prize with David Thewlis and Michael Kosterlitz for theoretical work on topological phase transitions and topological states of matter. Just to refresh people who might have forgotten, as you are aware, topology is a branch of mathematics where we study properties of systems which remain the same if small changes are made in the system. In the same way, we have systems in physics which remain robust and can withstand small changes in the Hamiltonian. And one of the earliest of such manifestations was the quantized Hall effect, where the Hall resistance was found to be quantized by Klaus von Klitzing in the early 1980s. Later, David Thewlis, who actually shares half of this Nobel Prize, in 1988, in a model widely known as TKNN model, introduced simple periodic potential in the flat portion of the potential. Haldane in 1988, but I must tell you that today's speakers probably will not be touching that part of Haldane's work, extended Thewlis's work on quantum Hall effect and showed that similar effects would occur in semiconductors even without a magnetic field. However, our speakers today would review another important aspect of his work of the 1980s on antiferromagnetic spin chain. And this is actually where I come in, because there was a lot of work done in 60s and 70s on spin chains, but they were primarily limited to spin half chains. In fact, that was my PhD thesis of 1971. So it was believed that if instead of spin half, you considered integer spins, the systems would behave more or less the same way. In 1983, Haldane used topological techniques to show that these two types of chains have very different properties. So what I understand is both Professor Mahajan and Professor Pujari will be talking about the spin chains primarily, and both the experimental and theoretical aspects. And so without more ado, I hand over the platform to them. Thank you.
Okay, thank you. Maybe I'll start, Professor Suresh.
Thank you, Professor Ghosh and Sumiran. Yeah. No.
Yeah. Okay, is my screen visible?
Yes, yes.
Okay, good afternoon, everyone. It's wonderful to have this opportunity to talk about our convocation speaker's work, who is also a towering figure in my particular field of research, which is quantum condensed matter theory. And today I will tell you a story which led to his Nobel Prize, and it is titled Haldane's spin chains. So this is that part of the work. So to set the stage, we often like to have some classical models or pictures in our head. And even for magnetism, which is the context today, there is a classical model or mental image that we keep in our minds often, especially when we see them for the first time in our high school or undergraduate textbooks. So especially if there are students here, undergraduate students, you might remember these kinds of diagrams where there's a circulating current, which has an associated dipole moment, or sometimes we draw this small bar magnet, which gives a dipole moment, magnetic moment. And we have an image that these kinds of objects, dipole moments, are present in our magnetic solid, and then they organize to give some form of magnetism. So in this diagram, I've shown examples of ferromagnetism and what is called a paramagnet, which is without any ordering. There is no organization of these microscopic dipole moments. And of course, these classical images, classical models are very useful, but the reason why they work is very interesting. And so we can be even more simple-minded when thinking, especially from the point of view of a theory. So what had been done prior is that one could be even more simple-minded. One could consider what is called an Icing spin. So it is not even a dipole moment, which is generally a vector pointing somewhere in space, but this Icing spin is just, it has two values, quote unquote up, quote unquote down, or plus or minus in different settings. They are called differently. And you can write down an energy function in terms of these degrees of freedom. This is a very famous model. That's why I wrote down this energy function. H stands for Hamiltonian, for those who know. This is called the Icing model. Very interestingly, this very simple model, which at the very first instance you might think should not have anything to do with magnets, turns out it can capture a lot about many magnets in nature. So in particular, the phase transition physics, when the magnet goes from an magnetized state to an unmagnetized state. And so there is a way, there's a whole subject of equilibrium statistical mechanics. This formula might remind you of that. That is employed, say, on this model, and you can understand a transition in a magnet. More sort of impressively, this simple model can capture something about a completely different situation, which is not even a magnet. It can capture some physics of the liquid gas transition that we see when we boil water on a stove top. So this is an example of the liquid gas transition data. Let's not get into that. But what is shown here is that various different liquids, when they go through this transition, if you scale things properly, they are essentially the same physics sort of represented in different contexts in words. So the reason why these simple models work in condensed matter when we try to explain the macroscopic properties of solids is what is now termed as universality. So universality really explains why simple models work. And this, just to give a brief review, so this concept originated with Lev Landau, who is a famous Russian physicist, another Nobel laureate, and he came up with the concept of what is called the order parameter. So it is really the order parameter independent of the microscopic details, which if it were to be non-zero, then we are in the ordered phase. And if it were to be zero, then we are in the disordered phase. And how we arrive at this order parameter is part of the detail. For example, I have some liquid, the atoms of the liquid have this much density, and that defines my order parameter, etc. But that's matter of detail. But as far as the macroscopic universal physics matters, it's really what matters is the symmetry of the system and the dimensionality, whether it is in 1 dimension, 2 dimensions, 3 dimensions, etc. So for example, in the context of the Icing model, this gives rise to what is called a scalar order parameter, which is just a number, a real number. Importantly, if we look at this model, if we think about it a little bit, you can convince yourself that it has this particular symmetry, that the order parameter, when I just flip the sign of this order parameter, the energy function will remain invariant under it. And therefore, if I want to write down an effective theory to explain the macroscopic properties, I will only allow terms which are invariant, which are left invariant by this particular symmetry. So, and then we build a theory, and this is how Landau built the theory of various phase transitions and many others following him. But it is this reason that once I have the symmetry and the dimensionality, I'm really constrained to write only one kind of theory. And that's what gives rise to the universal macroscopic physics. I don't have much freedom after that. And so this led to this, what is now called as the Landau or Landau-Ginsberg framework. This was before the topological era. So this is the modern, more nuanced understanding of what a phase of matter is. And really, we characterize a phase of matter by these order parameters, and in particular, the correlations that these order parameters have. So deep inside order phase, these order parameters, the correlations in them exponentially decay to a constant, whereas deep inside the disordered phase, the correlations decay to 0. So eventually, when they're far enough, there is no correlation among the orders. So example of the disordered phase is, for example, a gas, whereas example of an ordered phase is solids, liquids, magnetic phase, etc. And very interestingly, near the phase transitions, these correlations actually have different functional forms. They show power laws, and this is another manifestation of universality. So all this way of thinking constitutes the understanding of phases of matter. And so this was originated by Landau, but Ginsberg also played an important role in how to think rigorously about fluctuations of the order parameter. And that's why his name is also associated with this. So this basic idea is what we keep in mind at a more rigorous or a more theoretically advanced level when we think about magnetism. But when we come to the dipole moment that I introduced in the very beginning, then the order parameter, now you can imagine, because the microscopic dipole moment is a vector, the order parameter also has a vectorial nature. It's a vector. And therefore, the symmetry now is not just the sign flipping symmetry of the Icing case, but rather it has a full rotational symmetry. I can fully rotate this order parameter, and the free energy or the energy function has to be left invariant. And so this is a very important difference. And this again connects back to the whole Landau-Ginsberg framework, that symmetry is really the key to describe the universal macroscopic physics. In this case, when I have rotational symmetry, we know that this is a continuous symmetry. I can rotate the order parameter by any angle around any axis that I want. And this gives rise to, in a magnet, what are called spin waves. So spin waves, as shown in this diagram, are modulations of the spin order parameter, the vector order parameter, and you can make the wavelength as long and the deviations as small, and so they don't cost much energy. But of course, since there are many possible such spin waves, they have what we call entropic contributions, meaning they want to disorder the system. And very interestingly, in 1D and 2D, it was shown by Mermin and Wagner that these low energy spin waves is sufficient enough to destroy magnetic order. This was a rigorous, this is a result at the level of a theorem. It was quite remarkable when it was first understood. And in fact, historically, this idea goes back even before Piles had shown that just simple solid formation in 2D is not possible due to similar arguments. There are some low energy modes in the system due to thermal fluctuations. The thermal bath just keeps making a lot of them, and they disorder the order that the system would have wanted to obtain. Thus, in 1D and 2D magnets, classical dipole moments, they cannot order according to Mermin and Wagner, and therefore there cannot also be any ordering to disordering transition either. However, in 3D, the Mermin-Wagner argument does not work, and actually classical magnetic order can survive. And that is how you can rationalize that this mental classical model of a magnet actually works. So it is in this context that Kostelis-Thouless and Berezinski result was very impressive and very surprising. So this is the other part of the Nobel Prize work, which is not the focus, but just to set the background. It turns out that this work was very crucial to even for Haldane's work. So in 2D, what Kostelis and Thouless showed, and even Berezinski in two different sets of work, that there can be a transition in 2 dimensions which was completely unexpected at that point of time. And it works for a vector order parameter, but that vector order parameter is furthermore a planar vector order parameter. So for example, arrows in the two-dimensional plane as shown in this diagram. And so it was then understood that this is not an usual ordering to disordering transition of Landau-Ginsberg, but it is at this point really when topology made its entrance into condensed matter. And this was one of the reasons why this work was recognized by the Nobel Foundation. And so in 2D with a planar vector order parameter, apart from those low energy spin waves that we saw before, you can have these new kinds of defects, these vortex-like defects. These are topological defects in the system. So these two examples, of course, many of you would have have an intuitive understanding of what a vortex is. For example, when water goes down the drain or something like that. So these defects now are play an important role in the physics of the system. And the topology of this is sometimes captured by this idea of a topological invariant. And you can see that this winding of the spin or the vector order parameter, it winds clockwise 360 degree in one diagram and maybe anti-clockwise in the other diagram. So this fact is unchanged by any smooth deformations of this vector field or this diagram. And that's why this is called a topological invariant. And it is these topological defects which actually could potentially give rise to a new kind of transition in 2 dimensions. And it was understood that really this transition that was claimed in 2 dimensions should be understood as a unbinding transitions of these topological defects. So there is one phase in which these topological defects have unbound. They are just freely proliferating everywhere due to thermal fluctuations. Whereas in the other phase, they are strongly bound together, and you don't have them in your equilibrium ensemble. But since Mermin Wagner had taught us that there cannot be ordering, so what is this phase where the topological defects are bound, have not proliferated? They are actually signaled by only power law correlations in your order parameter, whereas standard ordered states have exponentially decaying correlations which decay to a constant, as I mentioned before. But to be consistent with Mermin Wagner in this Kostelis-Thouless scenario, BKT scenario, they only have power law correlations. And so this work was recognized by this Nobel Prize as well. And so, of course, this is at the level of theory, but these planar vector order parameters are actually relevant for various experimental situations. And in fact, the BKT work was inspired and motivated by these experiments. And furthermore, once the theory was developed, after that, various experiments, in particular Bishop and Reppe, confirmed this picture. So in this background, now I go towards the topic of quantum spin chains, which is where Haldane played an important role. So now we come to the quantum mechanical setting. So in quantum mechanical setting, fortunately or unfortunately, these classical models or classical images that we have in our head, they are just not valid or applicable anymore. Fortunately, because it gives rise to new physics, and unfortunately, because we like having classical images in our heads. In fact, so the one wonderful thing for me was towards preparation of this talk, I spent some time reading Haldane's and Kostelis' Nobel lectures and some videos. And Kostelis remarked that he was initially in high energy, and before this work, he had always tried to avoid statistical mechanics, thinking that was an extra detail. And once he got into statistical mechanics and BKT physics, he has in his life tried to avoid quantum mechanics because that's the next level of complication. But Haldane, of course, went ahead in that direction. So the degree of freedom in quantum mechanics, we know that it actually is a Hilbert space. It's a different kind of space than the classical phase space. And because of this feature, qualitatively new physics can arise. So at the level of Hilbert space, What a new thing that can arise is what is called the Berry's phase, due to the fact that it's a quantum Hilbert space. And a simple way to understand this Berry phase is that your degree of freedom, for example, the quantum spin, it does somehow, you arrange for a cyclic time evolution. It starts at some time point and then does some evolution and returns back to the same state at the initial time, at the final time. It's the same state, but it can acquire a phase under this evolution, which is, I've called it as e to the I phi. And this is what is called the Berry's phase. The point is, of course, an overall phase does not affect the probabilities, but it can bring in new quantum interference effects, which we know very well from double slit experiments with electrons and even of light. Therefore, these Berry phase effects in a quantum setting can bring in qualitatively new physics for quantum magnets. And similarly, Berry phase effects in other contexts, other quantum contexts, play important roles. And in this context, in the context of quantum magnetism, Haldane played probably the pioneering role in initiating these kinds of new ideas. So before we set the stage for Haldane's work, just some info on 3 dimensions. So just as Icing model was a very simplified model with the hope that it will capture some universal physics that we see in nature, for quantum magnets, the Heisenberg model is that simple model that you hope can explain the universal physics that you see in some solid which has these quantum spin degrees of freedom. So this is very analogous to the Icing model. It has, but it's a vector. The quantum mechanical spin is also like a vector because it's an operator for those for technical reasons, and it has the form S dot S. Again, importantly, from the point of view symmetry, I can continuously rotate these symmetries and the energy function won't change. So there is that idea of symmetry and dimensionality playing a role. If J is less than 0, this coefficient, then the spins want to align themselves. Let's not worry too much about the details, but for a certain parameter choice, the spins want to align themselves, and that's what we recognize as a ferromagnet, whereas when J greater than 0, the spins anti-align themselves, and this is what we think of as the antiferromagnetic state. It turns out in the quantum case, there is a conservation of the total spin along the magnetic field. This is due to the quantum mechanics of the problem. And therefore, ferromagnetic order actually is unaffected by quantum fluctuations. So this is a new ingredient when we come to the quantum setting. In the classical setting, when we are studying classical statistical mechanics, the thermal bath brings in certain thermal fluctuations. But in quantum mechanics, we have what are called the quantum fluctuations. However, this ferromagnetic order parameter is unaffected by that. And so therefore, ferromagnetic order is more robust in some sense, whereas antiferromagnetic order actually, it turns out, is not a conserved quantity for this Heisenberg model, and therefore it will be affected by quantum fluctuations. And it turns out this actually was important in the history of observation of antiferromagnetic order, because Lev Landau, the same Landau, had actually objected to the initial claim of the observation of an antiferromagnetic state in 3 dimensions. So of course, the antiferromagnetic state is not a regular magnetic state which has a large magnetic moment that you can stick to the fridge magnet. It has no net magnetization, and so therefore it is a subtle state, and it is again from the in the Landau-Ginsberg framework that it is the antiferromagnetic order parameter. Its correlation should decay to a constant. That's what really constitutes order. Therefore, when Louis Néel claimed that he has observed antiferromagnet based on some bulk observations, not really studying the correlations of this order parameter, Landau had objected to that, saying that quantum fluctuation should actually destroy it. And it turned out that finally scattering experiments, which really measured the correlations between the order parameter, the antiferromagnetic order parameter, settled the debate. And from a theory point of view, in 3 dimensions, actually, what are called spin wave theories, they do a great job. Meaning, so what a spin wave theory is, you have your ordered state. On top of that ordered state, you have these low energy spin wave modes. So they cause some, they bring in some quantum fluctuations, and in presence of a thermal bath, they bring in some more thermal fluctuations. However, the order does not get destroyed, and you can build a quantitative theory with this with this basic picture, and you can explain on many features of the experiment. It turns out, for technical reasons, in spin wave theories, the spin actually is almost the exact value of the spin, whether it's in quantum mechanics, the spin only takes discrete values, spin half, spin 1, spin 3/2, and so on. It doesn't much matter. In fact, in a spin wave theory, it is really a continuous parameter. It need not even be discrete. So it was in this background that really Haldane's result or prediction was really remarkable when he wrote in 1983 and even in 1981 that spin equals half, 3/2, 5/2 are qualitatively different than spin 1, 2, 3. In particular, for these half odd integers, half, 3/2, so on, he predicted that you should have a gapless ground state with power law correlations, very reminiscent of the quote unquote ordered state of BKT, Kostelis Thouless. Whereas for the S equals 1, 2, 3, or half even integers, he predicted a gapped ground state with exponentially decaying correlations. So since it seems as if that the microscopic information about the degree of freedom, the value of the spin, seems to matter, it is in this sense that it is beyond the conventional, at that point, Landau Ginsberg framework. And the arguments that led Haldane to this prediction was really based on a field theoretic way of thinking, which was somewhat new to condensed matter, but they of course were prevalent in the particle physics or high energy literature. But historically, it is at that point in particle physics, people write down Lagrangians, whereas in condensed matter, people had mostly stuck to Hamiltonian way of thinking. The Lagrangian way of thinking came into condensed matter. And Haldane mentions that it was in a conversation with Ed Witten that he realized how certain extra terms in the Lagrangian are allowed in presence of quantum mechanics, which can make a key difference. So the key point is that in quantum mechanics, you can have quantum interference processes due to Berry phase effects, which are really different for half even integers and half odd integers. And this basic observation underlies the prediction of Haldane. And so this is where we can recall, for those who have done quantum mechanics 1 or 2, there's this very interesting result that for a spin a half, if the spin half is rotated by 360 degrees, then it causes a sign change. The state actually acquires a sign. Whereas if you have spin 1 and so on, it does not acquire a sign. So it's for those who have undergraduates in the audience, those who have seen this result, just keep this in the back of the mind when you see the next few slides. So how to make sense of this this quite remarkable claim, which was completely unexpected at that point in time, when the understanding was that you mostly have antiferromagnetic states, a nail state, up, down, anti-aligned spins. But here Haldane comes along and says that there's a gapped ground state which has no exponentially decaying correlations. So in this context, Haldane actually made another crucial contribution, which is called the Bozonization. And so this is, of course, I can't do justice to it, but just very briefly speaking, this is a way, so this is a very familiar technique often used in theoretical physics, where we take a problem and maybe we can't make progress with that problem, and we try to map it to some other problem that we can maybe make progress on. And so it really boils down to such mappings that were this Bozonization way of thinking was really such a mapping, and you can ascribe it to essentially what can be called the magic of quantum Hilbert spaces. And this is a technical step, so I won't go into it. But just to have at the back of our minds, when we first learn about harmonic oscillator, our very favorite quantum harmonic oscillator in the first course of quantum mechanics, we are introduced to the Hilbert space of the position and momentum. This is some continuous Hilbert space, and we have an algebra X. The commutator of X and P is IH cross, which is a very important relation in quantum mechanics. But then we introduced the eigenbasis of the harmonic oscillator, which is the creation annihilation operators and their algebra, the commutator of A dagger, the creation and annihilation operators equals 1. But it is really the same Hilbert space. There is no different Hilbert space. We are talking about them in different languages. And even more remarkably, for 1D spin chains, in one dimension, spins can be mapped to fermions, fermions can be mapped to bosons, and it's really this magic of Hilbert spaces which allowed Haldane to make some progress. And so this way of thinking had precursors before. Other people had thought about this, and it turns out in one dimensions, even exact computations are possible based on what is called the Bethe-Ansatz technique. And it is very interesting that Haldane was actually trying to reconcile the Bethe-Ansatz results with existing results which had discrepancy, and that really led him to formulate his way of thinking about bosonization, which then made sense of all of the issues at that point of time. So for our purpose, to understand the claim of Haldane, often what we do or what we say is that a quantum problem, the time evolution of a quantum problem in d dimensions, can be mapped to a classical statistical mechanics problem in d+1 dimensions. So very roughly speaking, the quantum evolution e to the I minus it of the Hamiltonian is formally analogous to e to the minus beta h, which we saw before. This is the fundamental structure that we have in classical statistical mechanics. So it's as if we have on the quantum side, it's as if there is a imaginary temperature, and it is in this sense that I can think of the quantum problem as a classical problem in one higher dimension. So Haldane, what he did is to show that using bosonization, he could map the 1D spin chain problem, say spin half, spin one, etc., to actually the 2D classical setting of Kostelis-Thouless, Berezinski-Kostelis-Thouless, which is completely remarkable. But that is what was achieved in a theoretical step, quite impressive step. And therefore, the final understanding was that the gapless ground state for spin half is really, one should think of it as the ordered phase of the Kostelis-Thouless, where also the vortices were bound to each other. And so therefore it was a different phase when the vortices were unbound. But to reconcile with Mermin-Wagner, the order parameter could have only power law correlations. So what Haldane explained is that this gapless, for half odd integers, the gapless ground state with power law correlation should be thought of that quote unquote ordered phase of Kostelis-Thouless. And the reason is, of course, under the mapping. So in the Kostelis-Thouless picture, we had these new defects, the topological defects, the vortices. So actually, they are also present in this quantum problem, but under this quantum to classical mapping. So this 1D spin chain actually maps to a d+1, so 2D classical problem. And so one direction is the 1D space, and the other direction is the imaginary time or the time. And the vortices are really, to think about it from the point of view of the time evolution, they're really a tunneling event, which we first learn about when we learn about quantum mechanics. So at this time instant, it is one kind of an antiferromagnetic configuration. And as I go along, you see that it has flipped over. And so there is this event, this tunneling event, which was all these kinds of processes, tunneling processes, were also known in other contexts, and they were called instantons in high energy literature. This tunneling event is the analog of the vortex in Kostelis-Thouless. But the point is, in the quantum setting, you have Berry phases associated with these processes. And then, okay, maybe I'll skip this. This is part of the argument. If you analyze this diagram, if you have a vortex at this point in time, and then if there's a vortex on a neighboring bond, you can see that this site, the way the spin rotates in this time evolution, it actually rotates by 180 degrees clockwise in one case, then it rotates 180 degree counterclockwise in the other vortex configuration. This is a technical step, so it might be confusing. But but the point is, from the point of view of this, because we want to think of it as a classical statmic problem, but now there is quantum interference happening. So the quantum interference physics is the following, that these two vortex configurations, which are on two neighboring bonds, for between them, it's as if the spin has rotated on the side that is shared by the two bonds. The spin has rotated by a full 360 degree. Because in one vortex configuration, the spin rotates by 180 degree clockwise. Then in the other vortex configuration, the spin rotates 180 degree counterclockwise. So it's when I compare the two cases, that spin actually has rotated by a full 360 degree. Therefore, the relative phase difference between these two tunneling events or processes is actually a phase of -1. And so therefore, they destructively interfere, just as happens in some diffraction experiment. So therefore, these single vortices are actually, they sort of destructively interfere with each other, and it's as if they are just not even present in the classical D+1 two-dimensional problem. And so therefore, the allowed processes are what are called double vortices, which is just two vortices present in my space-time configuration. And so therefore, the power law behavior of the spin half chain is really the ordered side of the Kostelis-Thouless physics, where with only doubled vortices allowed. Whereas the original, in the first half of the talk, the classical Kostelis-Thouless physics I talked about, their single vortices were also allowed. So this also explained the gap opening on the Icing side. This was another sort of power of this way of thinking. Because these are doubled vortices, the vorticity of the space-time configurations can only change by 2, and therefore there are two different distinct sectors which are connected by these tunneling events, say vorticity of 0, 2, 4, and so on, and vorticity of 1, 3, 5, and so on. These are two distinct sectors. They all intermix with each other due to tunneling events, etc. But these two distinct sectors lead to a gapped state once they unbound, and this leads to some expected degeneracy of 2 on the Icing side. So on the Icing side, there are two degenerate configurations. One is up, down, and the other one is down, up, down, up. So this way of thinking explains that degeneracy also because of this doubled vortices. And finally, to even more interestingly, in the spin equals 1 and in the integer, half even integer cases, this quantum interference process that I described before for spin half actually doesn't exist, because the phase acquired by these when the spin rotates by 360 degrees is just 1 and not -1. And so therefore, these vortices actually constructively interfere, i.e. they are actually present in the classical statmic problem. So therefore, the single vortices also are part of the problem. And now it is actually the standard picture of the Kostelis-Thouless physics with single vortices that I mentioned in the previous part of the talk. And so therefore, for spin 1, the picture is binding, unbinding of these single vortices. And when the vortices are unbound, there is only a single disordered state, because these vortices connect all winding sectors, 0, 1, 2, 3, and so on. And so therefore, the understanding was that for the spin 1 chain and spin 2 chain and so on, there is only one single disordered ground state. And this is just the ground state obtained by the proliferation of these topological defects. And there is this unique gapped ground state, which was called the topological spin liquid state. And then you might ask, of course, that there is this unique gapped ground state, but where are the power law correlation phase of the Kostelis-Thouless? It turns out that you have to tweak the Hamiltonian so that you go towards what is called the easy plane limit, where you don't want the spins to align along the magnetic field direction, if you wish, but perpendicular to the magnetic field direction. And then if you tune towards that direction, you get power law correlation phase of the BKT. And if you go towards the easy axis limit, then you again get an Icing transition based on the Icing model from this disordered topological spin liquid state to the twofold degenerate Icing antiferromagnetic state. And so this was the sort of really a theoretical masterpiece of work that Haldane set up, and which was led to his Nobel Prize. So with that, I will conclude. So before I conclude, especially for the students, I would like to mention that, of course, there was a lot of theoretical jugglery and theoretical arguments and reasoning, which is not, which almost might have felt like science fiction. And even when I try to work some of these things out, sometimes it feels like science fiction, but science fiction, of course, has certain kind of power. And the even more powerful thing is that in this case, it actually pertains to reality. So with that, let me conclude. So the previous things that we talked about, but phase transition and phases of matter, which were driven by topological defects with distinct quantum interference properties. And this was recognized as an important work by the Nobel Committee. This quantum spin change is a field of study within quantum condensed matter. And soon after Haldane's prediction, this claim that half odd and half even integers were distinct categories were verified both in experiments and numerical computation. And the experimental aspect, my colleague Avinash will talk about. But as Professor Ghosh mentioned, that Haldane played another important role in topological states of matter. Let me skip that. But it led to the recent revolution of topological insulators. And let me end on this slide. I want to advertise the quantum magnetism action that is happening in our department, especially for the students, both in our department and outside. You might see us as instructors who are teaching you something or trying to evaluate you, etc. But we are also involved in trying to play a role in the frontier areas of physics. So in particular, Shomo Bera is studying non-equilibrium physics of 1D spin chains. Hitesh Pal has recently studied magnetism in 1D ladders. Myself, I have not studied quantum spin chains, but I have more focused, my work has focused on two-dimensional quantum magnetism and ordered and disordered states, etc. And even in experiment, Avinash's group has worked a lot on 1D and higher than 1D quantum magnetism, which he will talk about, where I have been fortunate to collaborate with him. But there are many other areas in the department which are more on the semiconducting and metallic side. There's a lot of work, and you should feel free to come and talk to us and even join us in our effort. So with that, thank you.
Thank you, Sumiran.
Thank you.
So any discussion after Professor Mahajan's talk, right?
I'm open to if someone wants to ask a question or something.
Swami, any questions are there?
No.
So then maybe Professor Mahajan, yeah.
No hands is raised. So
Okay.
So shall I go ahead, share screen and?
Yeah.
Professor Mahajan, can't you share the screen?
It's coming.
Okay.
My laptop is nowadays rather slow, so
Okay.
I think it'll come up.
It's coming.
Yeah.
So you have to use IRITPP funds.
Yeah. Pretty soon.
Yeah, it is coming.
Yeah, and I mean, for me also, it's still coming. So.
Yeah. Yeah, it has come.
Yeah. So yeah, let me try to go to the slideshow mode. And also let me try to get a pointer if possible.
The right click of the mouse will.
Yeah, that's it.
Yeah.
Yeah, so good afternoon. So I think it's quite apt, and we have really a giant of condensed matter physics coming as a chief guest for our 58th convocation tomorrow. And then it's apt that we have a prelude to this and giving some introduction to the essence of his work, over the last, 20, 30 years or so. Professor Ghosh and Sumiran have already given a very rather broad background of his work. What I will do is I'll really focus on a specific aspect. So about this half integer and integer spin chains. Of course, he has contributions associated with integral quantum Hall effect, topological insulators, and also, of course, spin chains. So I'll focus specifically on these spin half, spin one chains, antiferro chains. So as Sumiran already introduced, half integer and integer spin Heisenberg antiferromagnetic chains, they're quite distinct from each other. And what does the theory say about that? So he has touched upon this. I'll maybe give a little bit more detail. So one thing is clear that these spin chains, antiferromagnetic Heisenberg chains, they have rather novel ground states and novel excitations. And, very broad implications. So as you saw, you can map one thing to the other. The Kosterlitz-Thouless phase is little like the spin half chain or the spin one chain, depending on various things. So the final issue is: are there real materials which exhibit these kind of properties? Okay, so of course, we are here. It turns out there are indeed materials which exhibit such fascinating properties, and so I'll give some examples. And the other point I would like to address is: how can you actually probe the properties of these pristine materials by actually putting in defects? Okay, so let's close this. And so, one doesn't have to go to very fancy advanced books or anything. Just go to Ashcroft and Merman's solid state physics. You open the chapter on magnetism, you find a statement there. Finding the ground state of the Heisenberg antiferromagnetic is an unsolved problem, except in the special case of the one-dimensional array of spin half ions with coupling only between nearest neighbors. So this was the beta ansatz which Sumiran talked about. So the ground state was known. The excitations were worked out, but there was some disparity between that and what was known from spin waves. Additionally, the other thing also Sumiran talked about is this now well-known Mermin-Wagner theorem, where he basically said that in one dimension or two dimensions, in isotropic models, you cannot get long-range order. It's prohibited. And again, the textbook of Ashcroft and Mermin gives a simple qualitative way of understanding, where if you assume that the spin wave excitations are valid excitations, then they're actually strong enough to totally destroy the magnetic state even at t equal to 0 for 1D. Okay, so this is one point. So outcome of all this is that this 1D Heisenberg antiferro chain does not have long-range order even at t equal to 0. So just picture this: you have small tiny magnets sitting next to each other on a chain. They have strong interactions with each other, which wants to align them anti-parallel to each other. But even you are at t equal to 0, when there is no thermal energy, still they are unable to order in some fashion. Okay, so this is because of these quantum fluctuations that are present. So this ground state is a macroscopic singlet which entangles all the spins. So this is the buzzwords which have appeared over the last maybe 5, 8, 10 years in solid state physics. So this represents some entangled state. The other interesting thing is that the excitations from this ground state, whatever that is, are not spin waves. One pictures spin waves as when you're away from t equal to 0, the individual magnetic moments precessing about some field direction, and a specific phase relation between the neighbors, and that gives rise to a spin wave. So, but in these spin half or spin 1 chains, spin waves are not valid excitations, but they are something different. They are spin half excitations, and they have been given the name spin-offs. So, are real systems which are 1D? Is there a difference between the properties of spin half and spin 1? So, indeed, both the situations are true. They have been observed. So, we'll focus on that next. So, here is a caricature of a integer spin, so spin 1 chain. Okay, so the relevant model here is called the AKLT model, for the 4 authors, Affleck, Kennedy, Leib, Tasaki, and they derived their inspiration for this model from the spin half chain model associated with Majumdar-Ghosh, okay, with Professor Ghosh talked right in the beginning. So they now consider this spin 1. So this here is a spin 1, and they picture this spin 1 as if it's made of a symmetric combination of 2 spin halves. Further, this is the neighboring spin 1. So how are they connected with each other? This spin 1 is made of a symmetric combination of 2 spin halves. And then the spin half that is over here is coupled with this spin half from the neighboring atom in a singlet state. Okay, so this is the solid blue line. So it's in a singlet state. So you have an up, down, minus, down, up type of wave function associated with this. While the one here is in a symmetric state. Okay, so this is a caricature of a spin 1 chain model. So this is not the Heisenberg model. Remember, Heisenberg model only has a SI dot SJ type of term. This has yet another term, but then for this Hamiltonian, which includes the biquadratic term also, they could solve it exactly. And then the feeling is that the solutions of the Heisenberg model are actually quite close to what this would be. So one interesting thing here is that, of course, if you look at this chain, since they're bound in singlet states here, you don't get any magnetic moment at all. But if you cut the chain, so for example, that is shown as a endpoint here, then this spin half here is left with no pair. Okay? You have cut it, so there's a neighbor on the left side, but there's no neighbor on the right side. So you have an edge state here, which you think might have spin. Similarly, on the other side also, if you have cut the chain, then the spin half here, there's no spin half really, right? There's a spin 1, but you imagine that as being made of a symmetric combination of 2 spin halves. One of them is bound in a singlet with the other, but then this one has no pair. So again, you get a spin half edge state. So these are very exotic sort of implications. You don't see these in normal magnetic material, right? So how are they actually seen in practice? So right here, one expects that if you cut the chain, you just get a free spin half here, you get a free spin half on this side. In reality, this is based on numerical work. The way it works out is a little bit different. So here it's a caricature of 2 representative situations. So you have a half integer spin chain, which, as Sumiran explained, has power law spin correlations. They actually fall off as 1 over R. And it's a situation where you have a non-zero spin susceptibility at t equal to 0. So there is no gap in the excitation spectrum. These are gapless. Okay. The other one is the integer spin chain, which has exponentially decaying spin correlations. So just like you have a semiconductor, where you have conductivity which decreases exponentially with temperature because there's a gap between the conduction band and the valence band. So similarly, here we are talking about spin excitation. And here there's a gap between the singlet state, which is the ground state, and the triplet state. And so at t equal to 0, when there's no thermal energy, you don't get any magnetic susceptibility. So these are gapped ground states. So in the 2 cases, if you cut the chain, then there are effects on the neighbors. Interestingly, in the integer spin chain, the correlations fall off exponentially. So the effect of cutting the chain is to give rise to a staggered magnetization on the neighboring magnetic atoms, and that magnitude falls off exponentially as you go. In contrast, in the half integer chains, it has a strange sort of behavior. You have a staggered magnetization which actually goes up and then comes down, and then there's basically a power law. So these are very phenomenal, novel sort of predictions for systems where ground states are either gapless or gapped. Excitations are very strange. They are spin-ons. They are not the usual spin waves. The staggered magnetization that is induced because of cutting the chain or some such thing. It has a very strange sort of variation in space. Okay, so we would like to see in real systems where this kind of thing is observed. Is there a proof that this actually is true? So here is one example we looked at long ago. Actually, my first PhD student looked at this. So this is a system. So we always have to deal with some chemical systems to finally look at magnetism and whether these predictions about what the ground state is, what the excited state is, are they actually borne out in experiment? Can one actually make a ideal one-dimensional situation where there's no interaction between atoms in other directions? So these are all questions one has to explore. So here is one situation where you have a chemical which is an oxide containing yttrium, barium, nickel. Okay, so if you just apply common rules of electronic configuration, you'll find that the only magnetic atom here is the nickel, and it has an integer spin 1. Okay, and in the structure, so this is a schematic of the crystal structure. In the structure, the cyan atom, nickel atoms, they lie in a chain separated by oxygen atoms in between, and the other chains are apparently quite far away. So it turns out, so this is, we know after doing the experiments, that this is a rather good example of a spin 1 Heisenberg antiferromagnetic chain. So it's really a chain-like system. There is no interaction between the chains. Okay, so the antiferromagnetic coupling actually happens through the oxygen in between. So you have nickel orbitals which overlap with the oxygen orbitals. Those oxygen orbitals overlap with the next nickel orbitals, and that's how this so-called super exchange interaction arises. Okay, these nickel oxygen chains, they are separated by the other bigger atoms in other directions, and so they give rise to a situation where you can treat them as isolated chains. Okay, so what are the properties of this? So we'll come to that. Before that, I would like to just give a very quick introduction to a local probe technique, which we have used to find out, issues about what the ground state is, what the staggered magnetization is, how it changes as a function of temperature, etc. So the key here is that we want to look at a nucleus which is indirectly affected by the magnetic moments. Okay, so nuclei have magnetic moment. So nuclei have a spin. So there's associated spin degeneracy. So this is the simplest case of a nuclear spin half is what we have shown here. So if you apply a magnetic field, the spin degeneracy is lifted. Now, on top of that, if you now apply an RF field, you can pump energy into the system. And if your energy is equal to the energy level separation of the Zeeman split levels, then you can actually have resonant absorption of energy by the system. Okay, so this phenomena goes by the name of nuclear magnetic resonance, because you are exciting resonance between the various nuclear spin levels. Now, how is it useful for our situation? It's useful in the following way. So one has also a classical picture of the nuclear spin precessing about the applied field, and the precession frequency omega is given by a gyromagnetic ratio of the nucleus multiplied by the applied field. Okay. Now, so if you know the applied field, this gyromagnetic ratio is by now a well-known quantity for all nuclei. Okay, so the resonance frequency is well known. However, in an actual material, there's also an internal field. Okay, this internal field arises because you have magnetic moments, right? So for example, here you have nickel magnetic moment. So that nickel magnetic moment gives rise to an internal field at whatever nucleus you are looking. So this changes the resonance frequency. The change in the resonance frequency is proportional to the internal field. So it's proportional to the magnetic property of the system. Okay, so our intention is to probe this resonance frequency shift as a function of temperature in the material. Okay. So as I've noted here, this internal field comes from the intrinsic magnetism of the material, by which the resonance frequency gets shifted, and we would like to track the shift in the resonance frequency to probe the internal magnetism, intrinsic magnetism. Okay. Now, how is it useful, and what is the layout in the given system? It's as follows. Okay, as I mentioned, you have these nickel oxygen nickel chains. Okay, so they are here like this. They don't interact with each other. The nucleus that we are looking at is this one here, the atrium. It's also shown in this figure here. You have these chains of nickel. Okay, chains of nickel. That's your spin 1 Heisenberg antiferro chain. How you observe this magnetic moment? By sitting out here. The yttrium atom here, or yttrium nucleus here, is the resonance for which you are going to look for a shift. And so your probe, your SPY is sitting over here. It's going to look at this chain, but interestingly, it'll look at only one nickel from here and one nickel from here. So you're really doing a local probe of magnetism. One yttrium looks at only one nickel of the chain. So you will really be able to probe the magnetism of a specific nickel. Okay. So this is the intention. You want to probe the magnetism of this so-called Haldane chain compound using this local probe. So initially, a bulk measurement actually gives you a variation of something called a magnetic susceptibility. It's just how much magnetism can you induce by applying a magnetic field, right? So you apply a magnetic field, measure the magnetism of the material, and measure it as a function of temperature. Okay, so you get something like this. So you can make out here that there's a decrease here. So as it was mentioned several times, so these systems have a gap in the excitation. So just like in a semiconductor, the conductivity would decrease exponentially as you go down in temperature. Here, the magnetic susceptibility would go down exponentially as you decrease temperature. This is very nicely seen by NMR also, where you see a nice exponential decrease of this frequency shift, which I talked about in the previous slide. And one can obtain a gap from the exponential variation of the intrinsic magnetism. Okay, this gap one can determine, and for this system, it comes out to be some 85 Kelvin in units of temperature. So exponential decrease of the susceptibility due to a gap, as was predicted by Haldane for integer spin compound. The other thing you want to look at is what happens to the local staggered magnetization. Right? So for this, it's important to look at the following picture. So the ideal infinite chain, okay, at t equal to 0. Remember, this is a spin gapped state. So at t equal to 0, no thermal excitations. And there's a gap between the ground state and the excited state. Ground state is a singlet. Okay, so no magnetism. So if you were to look at what is the static moment at each side, each nickel side at t equal to 0, the answer would be 0. So each side has 0 magnetization for this infinite chain. But if you now somehow break the chain, okay, or put some substituent which is non-magnetic, which amounts to breaking the chain, it suddenly frees up static moments on the neighboring atoms. Okay, in what way? In a way such that the sum total of these moments is spin half, sum total of these moments is spin half. So breaking the chain releases static moments at sites around the defect, and they actually reveal the intrinsic properties of the pure system. So this variation would be exponential decay. You could determine a correlation length, compare it with what is expected from theory, and so forth. So again, going back, remember I showed this slide here where you have this infinite chain and you have this singlet between the spin half components of the neighbors. And then for the edge, you don't have a pair for this last one. You get the spin half edge state. Indeed, that's what happens. But the spin half is actually spread over several neighbors. Okay. So this second picture here, where you see an exponential decay of the magnetization, is actually seen. Okay, which I would like to show you next. So you see a ground state which is gapped, and then you go ahead and you want to look for an excitations because of the edges which amount to spin half. So these are these fractional excitations. So once again, I show here that if you put an impurity, if you break the chain here, then these neighbors are going to have some up and down static moments going down exponentially. So the nucleus which is sitting close to these will see a different local field. Okay, you have an applied field, then you have a local field because of what the nickel atom is here is providing it, and so we expect some difference in the NMR spectra when you put these defects. Okay, so here is the actual experimental measurement. So as you see, what happens, we substituted non-magnetic atom for the magnetic atom, so that amounts to breaking the chain. What is the result? You see the yttrium atom, which looks at this nickel marked 1, it sees an extra field, okay, because there's a static moment now. Earlier there was no static moment. The one at coupling to side 2 sees a smaller field, okay. 3 sees a larger but slightly less than the previous one, and so forth. So you expect that the resonance frequency of the various yttrium nuclei is going to be different. It's going to be shifted by various amounts, and you should see the contribution in this NMR spectrum from a different resonance frequency point. So the central line here is from most of the, you have very small amount of impurity. So most of the nickel atoms have 0 moment. So that is what is seen by this main line here. And then on either side, you see something seeing a higher field, something seeing a lower field. Okay, and you can actually figure out multiple near neighbors. Okay, so once you put this all together, one can obtain the static moment near the impurity as a function of whether you're at the first neighbor, second neighbor, third neighbor, and so forth. And you actually see this staggered magnetization varying exponentially. Okay, and as you vary temperature, of course, this changes. Remember that sum total is expected to be a spin half, and that should vary in a Curie-like manner, C by T as a function of temperature. And indeed, one sees that. So one can actually map this static moment as a function of temperature for the nickel sitting next to the defect, then 2 neighbors away, 3 neighbors, 4 neighbors, and so forth. And one gets the variation of the resonance frequency, from which one infers the magnetic moment. And then, as I mentioned, summing the above, okay, gives you the total susceptibility because of the edge spin. So you are actually seeing these edge modes here. One can sum all this, and one does indeed get something which is close to a spin half. Okay. So this was published. So as far as I know, Y2BA NiO5 is the only spin chain compound, integer spin chain compound, where this local staggered magnetization has been seen. Okay, so this was first seen by Tedoldi and others, and then we presented a very detailed analysis of effect of spin 0 and spin half impurities in the Haldane chain compound. This was largely the work of my first PhD student, Jaideep Das, and together with a French group, and this project was supported by an agency called Indo-French Center for Promotion of Advanced Research. And so this presents actually a very comprehensive measurement of local defect effects in a integer spin chain Haldane chain compound. So both the ground state as well as this edge excitations are documented. Okay. The other question you might ask is what happens in spin half chains? Remember, I showed you earlier in spin half chains, a slightly different pattern is expected for the local staggered magnetization. Something which goes up and down, but however falls in a power law manner, but also has this initial increase and then decrease. Okay, so it turns out that only one actually compound in experiment, which one specific research group got some evidence. So they determined what should be the NMR spectrum if you had the staggered susceptibility varying in this manner, and then it's expected to have some horn-shaped pattern like this. Well, it turns out that in this spin half chain compound, so this is a copper-based compound, it is a spin half one-dimensional Heisenberg antiferromagnet. It turns out that in this case, people didn't so far succeed to put defects by intention, by design. However, when you make these materials, there are some natural chain breaks that happen. And so you manage to see if you can zoom on some of these, you look at the base of the NMR spectrum, and you see these edges which are expected based on this simulation. So there is some evidence in spin half chain also. Actually, this is the only paper where you see the staggered susceptibility by a local probe technique. right? So this is basically a summary of a very narrow part of the prolific work which Haldane did. So just the part about spin half or spin one antiferro chain. And so this is what we focused on. So Haldane's work, of course, has spawned really exciting new areas. His work of nearly 40-year-old has spawned enormous number of areas in condensed matter physics. Of course, quantum magnets, which all of us are working on. Some of the terminology is also new. Quantum spin liquids, you get fractional excitations, edge states, also relevant for semiconductors, topological phases, entanglement. A plethora of new avenues have been literally invented by him. And we work on a, mere mortals like us, we work on some small, limited number of directions here. So here, for example, I, together with my students and postdocs, we've been working on also 1D, but now more 2D or 3D quantum magnets in various geometries. So more recently in various frustrated geometries like triangular and Kagome and so forth. One expectation from theorists is that doping these spin liquids, which are naturally strongly correlated, entangled, and so forth, might induce a novel ground state superconductivity. So we would like to explore this aspect. Of course, edge states in novel spin liquids have not been observed so far. Okay, this is something we would like to explore via nuclear magnetic resonance. A new area that has come up recently is that of Kitaev materials. So here again, you have a strong spin orbit coupling, which gives rise to very strongly bond-dependent interactions. And so again, novel physics, which somehow also comes out of Haldane's original work. So you have these Majorana excitations. Again, we would like to see this with local probe techniques. So we have various tools at our disposal. So we make these various materials, look at bulk thermodynamic properties, look at local probe properties by nuclear magnetic resonance or muon spin relaxation. And soon enough, we would like to also look at inelastic neutron scattering to look at excitations from the ground state. So with this, this is really a small part of what Haldane really invented in his work almost 40 years back. So, and I've tried to give you a flavor of what this looks like. And of course, another exciting area of quantum magnets. So as Sumiran mentioned, the various people in the department who work in various sub areas of this. And we look forward to, of course, new and exciting physics in the coming future. So thank you for your attention.
Thank you, Professor Mahajan. So Soumya, now you can take over.
Oh, thank you. So if there is any questions or comments or suggestions, either you can raise your hand or just unmute yourself and ask.
No questions.
So, Avinash,
Pujit, yeah.
I'm just curious about one thing. You showed this exponential tailing off of the behavior in those two graphs.
Yeah.
But the upper graph then suddenly turns up at zero temperature.
Yeah, very incisive. So you see, part of it is because of the edge states. The edges have, your natural material has chain breaks. So the edges have spin half. So they give a C over T.
Okay.
Which you see in the bulk susceptibility.
I see.
Yeah.
I see. And just a little pedantic thing I didn't understand on the previous slide where you wrote the spin configuration corresponding to the white ovals.
Yeah.
It looks more than just the symmetric state. There is something I didn't understand. If you just go back to, so you had...
Yeah, I know. So that's the AKLT. Maybe Sumiran can answer. It's just a projection where you remove the singlet.
I see.
And you just have the triplet ka 3 states.
I understand. All right.
Okay.
Thanks. Good, very nice talk. Thank you very much. Both of you.
Thank you.
Yeah. So, could I ask a question, Shomo?
Please go ahead. Shai.
So I was just curious, this is all new to me. I was just curious whether something interesting happens in even higher spin, like if I go to, a spin 5.5 or something like that. So, so spin 1 was discussed. So what happened? I mean, is there something that exciting that happens as you add more levels?
As far as I know, so the Haldane gap, for example, goes down exponentially with spin. It goes like e to the something s minus s. So it goes down very sharply. And I think there is some experimental work in higher spin. Spin 2, there's one material, but qualitatively there's nothing new. As far as I know, qualitatively there's nothing new. And the moment you go to higher spin, it becomes more classical.
But spin 5/2 will not show a gap.
Yeah, 5/2 not. So the spin half, but even going from half to 3.5 to 5.5, I think they get more classical.
Yeah, I'll also just repeat that qualitatively don't expect something, but the gap might be just too small to observe this physics. But what can make a difference is just the symmetry. The old considerations of symmetry and dimensionality, they can always make a difference. So spin chain and in 2 dimensions, whether it's a square lattice, honeycomb, all these things, the Berry phase is present, but how they add up makes a difference depending on the lattice structure and so on.
I see. Because this is the, so let me just say the motivation for why I was asking, because if you have basically SUN, then basically you can, of course, depending on how you bring back the spin, then you can have a gauge degree of freedom which is even higher than just U1. You can have a higher, and so in honeycomb, for instance, you typically have SU2 or something, and this playing with SU2 is part of the story here. So I was just wondering whether you could do it internally, or can you only do it geometrically, essentially on the lattice? So there seems to be a spin-dependent size of the effect which goes down, but then there is the other thing, which is the geometry, which is what you're saying, Sumiran, which is what others said as well.
Right. Yeah. So
just a minor comment. I think in Haldane's work, it's just geometry is just a line. So geometry doesn't really play a role. And in larger spin, just to answer your original question, actually becomes classical very fast because there's a factor of pi in the exponential, e to the minus pi s.
Yeah.
So there's a factor of 3 there, 3.14. So, really rapidly, you just start seeing classical physics. But as Sumiran was saying, if you are in 2 dimensions and you're on frustrated lattices, then it's very complicated and many interesting things can happen.
I see.
Yeah. Other questions?
Oh, hello. I have a basic question. Is when we are talking about the gap, what exactly gapped ground state? What does that exactly mean? Is this the gap between the ground state and the excited state, or and then then what does gapless ground state mean? It's a very basic. I didn't understand.
Okay, so yeah, so what you said is exactly right. There's a gap to the first excited state. So if you remember from your condensed matter course, right, when you have a gap to the excitation, for example, the specific heat decays exponentially, like in Einstein model.
Mm-hmm.
But if you have a gapless excitations, for example, phonons in a solid, they lead to this T-cube law, right, and so on.
Yeah.
So it can have implications whether you are gapped or gapless. Apart from the spin correlations or the order parameter correlations, they show up in your macroscopic thermodynamic, observables like specific heat and magnetization. And so on.
Okay. Thank you.
For example, for a spin half chain at t equal to 0, you would still get a susceptibility, magnetic susceptibility, because it's gapless. While for a gapped situation, you'll get 0 susceptibility.
Yeah, clear. I understand.
Other questions?
Just a comment. Sumiran and Abhinav both talked about Marmin-Wagner theorem, but as far as I recollect, that is strictly applicable for t not equal to 0.
Yes, you have the thermal fluctuations which destroy it finally. So yes.
Actually, yeah, that's a very interesting point. Actually, the qualitative idea remains the same, but the corresponding theorem for t equals 0, one dimension was actually proved almost 30 years after Mermin and Wagner. I think it's due to Pitaevsky and Stringari, because the technique needed for the proof is very different. Although qualitatively we expect the same thing to happen, the proof is actually very different.
Right. So for the students, the person who was speaking now is Kedar Damle of TIFR. So there is quantum magnetism action in Bombay, bigger than IIT Bombay. So should keep that in mind.
Also, he's from the campus.
Yes, and also he's a localite that way.
Kedar, are you going to share any tidbits from your interaction with Haldane when you were there?
Yeah, that may be an interesting.
Oh, well, no,
Kedar,
not really. I can tell you one joke.
Sorry, Hridish here.
Hi, Hridish.
Before you,
yeah,
before you get into reminiscing, to stay on the point, the comment that you just made, can you just elaborate a little bit on how the
Mermin Wagner?
Yeah, the t equals 0, what's
Yeah, so this is something actually, it's a very curious thing, because, you know, the basic way in which you think about it is the way Sumiran was saying. To imagine that there are these waves and they cost very little energy when the momentum goes to 0. And so then you just estimate by statistical mechanics how many of them are excited, and then a divergent number of them are excited. You expect the ordering to go away. That's the basic idea. Now, the way the mathematicians convert, or I mean, not mathematicians, Mermin and Wagner, how they put on a mathematician's hat temporarily and converted this idea into a proof. And the way they did that is they said that the long-range order parameter is bounded from above by a quantity whose denominator is the number of spin waves. And since that is diverging, you get 0 on the right-hand side of an inequality, and therefore the long-range order must be 0. That's how the proof works. Now, the proof involves the so-called Bogoliubov inequality, which you may have learned about in linear algebra. The students I'm talking to right now. And that requires a certain vector space structure and a notion of a metric. And the way Mermin and Wagner did that is they introduced this notion of inner product in the Hilbert space by basically looking at the non-zero temperature spectral sum to define an inner product. So the definition of the inner product they use to use the Bogoliubov inequality, that itself breaks down if you're looking at the 0 temperature one-dimensional case. So the technique of the proof has to be very different, but the physical idea we expect is exactly the same, which is what Sumiran was saying. So it's one of those curious things when you try to convert a qualitative idea into a proof. Sometimes you have to make a detour, and the particular detour Mermin and Wagner took involved defining this particular inner product that's only well defined for non-zero temperatures. And so I think the first people who figured out some other detour to make a proof work for the one-dimensional quantum case was, I think it's Pitaevsky and Stringari, and it's as late as the early 90s, actually.
Yeah, Stringari and Pitaevsky, I think so. Yeah.
I see. Okay, thanks.
It's again an inequality type of argument, similar in spirit, but different inequality, I think.
So what's the joke, Kedar?
It's not my joke, but since you asked. So when I was a grad student, we had a professor at Yale whose name was quite well known, I think, to everybody who reads textbooks in quantum mechanics. It's R. Shankar. And Shankar used to say that the Haldane gap, about which you heard, is the gap between Haldane and his audience.
Kedar, just to make sure, this is live recorded, huh? So you are now going, and might look at it.
It's a very famous joke. I think this is repeated endlessly. It's not my joke.
Yeah. In fact, Haldane himself says in his Nobel lecture that he had quite trouble publishing his initial paper, presumably because it was hard to, his description was hard for referees to understand, I guess.
He also says that, he's quite peeved that it's still called the Haldane's conjecture.
Yeah, that's the background to this joke.
Conjecture.
Actually, there is a real point behind the joke that Shankar used to make, which is that many people didn't understand the really revolutionary work he had done for a long time. And it took a while for it to percolate down. And so you're right. It used to be called the Haldane conjecture. Now, of course, we don't call it that. But for a long time, it was called that, I think. Yes.
In the lecture, Nobel lecture, he also makes a point. Maybe Mike Berry also deserves a Nobel Prize.
I see.
Just the very phase that you talk about.
Yeah, yeah. See, now it is there everywhere.
Yeah.
So, any more questions?
Okay, so yeah, there is any more question. So I have a thing to ask Sumiran actually. Sorry.
Yeah.
So you mentioned one small thing that when you talked about the Berry phase, actually, that you introduced the idea of Hilbert space. But strictly speaking, this Berry phase idea does not require quantum mechanics. Is this correct?
Well, yeah, more generally it is correct. But Berry phase is generally thought of in a quantum mechanical Hilbert space. But this idea of a
geometric phase, yes,
and sort of a anholonomy is more generally true. That's true.
It's even in a mechanical system, one can probably able to find this.
Sure.
Right. So there are.
Yeah. Even for classical rotations.
Classical. Yeah, I'm talking about classical. I don't need really. The dispersion.
This classical mechanics book by Griffiths, same of F.D.M. He actually talks about it. You set up a pendulum at the North Pole, then bring it down to the equator, then go along the latitude, then again go up. You get a change. So that's the Berry phase.
Right.
Quantum mechanics book. Quantum mechanics book.
No. Classical mechanics.
No.
Book.
Oh, classic quantum mechanics also it is there.
Okay, maybe.
Yeah.
Or maybe
the only time I've heard Berry lecture, he called it the Berry Pancharatnam phase.
Pancharatnam. Yeah, that's right.
Yeah. In fact, interestingly, Berry himself ascribed it for the first time to Richard Hamilton. So there are these conical points in the light field which are like a monopole defect of the Berry phase spin defect. So he called it. So he was giving a talk at ICTS, and he called because Pancharatnam, Berry, Hamilton, and he cited 10 different names who came up with this concept in different contexts. But to get back to Shomo's point, I think the key point was, of course, the idea of the geometric phase is more general, but in quantum mechanics, it leads to quantum interference. So that was the key physics process at play.
There is a review article by Shankar recently. I have seen it on Berry phase and all effects. Recent one.
Okay, I think.
I just want to
go ahead, please.
Non-physics comment. Just turns.
Professor Ghosh, you have to make the concluding remarks also, like
no concluding remarks. But see, I had known Mike Berry quite personally because I was a postdoc in University of Bristol, where I believe he's still there. But that's where he started his career as a lecturer. So he is always very mathematical. So one day on a rainy afternoon, he suddenly comes and calls many of us. He says, come, I want to show you people something. So he takes us to a bay window which he had in his room, and there's a beautiful rainbow there. So we thought he has called us to show us the beautiful colors. He says, do you see the airy function in the sky? That's what he told us. Okay.
Thank you, Professor Ghosh. I think I would like to thank everybody for joining here, especially Sumiran and Professor Mahajan for giving this nice introductory talk and on Haldane's work. Also, Professor Ghosh for joining. Kedar, thank you very much. And also all the other people who joined in this meeting.
There is a question by someone. Can you just...
Oh, I did not see. Sorry.
There are two actually.
Oh, yeah. I said, so is there any relation between the Haldane gap and Magnon-Bose-Einstein condensation?
Okay, if I understood the question, I would say not. So Bose-Einstein condensation actually more directly relates to the ordered ferromagnet or antiferromagnet, if you wish, thinking from the spin wave point of view. Whereas the Haldane gap is more of this topological spin liquid point of view in this path integral way that I talked about, or from a wave function point of view, it is what Avinash described of these spin ones fractionalizing into two spin halves, which form these singlet states. So maybe there is a point of view, but as far as I know, no.
Yeah, so there is another question. So the second question is there any rare earth-based spin-half chain compound?
I don't think so. Might be wrong. I don't remember seeing one.
Okay. Good. I think that. Thank you, Rama, for pointing this to me. With this, I think let's end the session. I hope all the students will join tomorrow for the econvocation. Again, thank you, all of you. And with this, I end this session.
Thank you.
Thank you.
Bye.
Thank you.
Bye, guys.